And so we'll talk about recursion now. And recursion basically allows us to go repeat the same structure, repeat the same process over and over. It can be kind of difficult if you haven't seen it before to wrap your head around it, just to be perfectly honest. So just know that some of this stuff can take a little time, but when you do have it, it helps us allow us to do a general function to go deeper and deeper when we don't know necessarily how deep something goes. So that's why recursion is super important. So what is recursion? Recursion repeats itself. So functions that call themselves, they're an alternate to looping. This is actually before looping, like for loops and while loops. Only programs were written in recursion, which definitely is a different kind of thinking. But like I said, it's best used for an unknown structure. When we use something like a while loop or a for loop, we usually know generally what the structure is. Recursion allows to have something where it's a little less certain and allows us to kind of basically go in as deep as we need to and then pop out when we're reach the bottom essentially. Okay. So some examples of how we could use recursion versus a for loop. Okay. It's like a sum of numbers. So a quick one is that we could basically take a sum of some numbers, right? So like let's say we have a range from 1 to 100. This is not technically a list, but close enough, right? We can define a function here. I take in my list, right? I say my total is 0, and then for each element in that list, I just add up to the total, right? And then return the total. So you can see here, if I run this, you can see here, it's like, okay, 7 milliseconds, 4,950. Like, okay, cool. You can also write a recursive function. So this is our first recursive function ever seeing it. And you'll see the structure is a little bit different here. In this case, I have 2 different returns, and it depends on what the condition is. So usually we'll hear like something like a stopping condition. So in this case, basically, my sum recursion, I say if the length of my list is equal to 0, basically there's nothing left in my list. Well, then obviously the sum of my list then would be 0, right? There's nothing in the list. So the list basically is empty. So it would make sense to return 0, okay? So if it's empty, say it's 0, okay? Otherwise, if there is something in my list, you're going to return my list 0 because there's got to be at least one thing in the list, right? Plus the sum recursion of my list, the rest of it basically. So from if there's one element to basically the end of it, right? So everything after that point, do the recursion of this. So if I do this, right, that's calling the same function here. And so let's say I have one element in here, right? So I have one element, let's say I have a list of like one element. Well, it would skip over this part, go to here. The first element, let's say it's the number 1, so it'd be 1 plus, and then say, okay, what's the rest of the list? This will be an empty list. So this will be an empty list. We 0, so it'd be for return 0. So this would be 0. So it'd be 1 plus 0, just give me 1. If there's 2 elements in the list, this is where it gets a little more complicated. Let's say there's 1, 2. So I'm going to write this down. So let's say, imagine our list has 1 and then 2. So the first time this gets passed into the function, it gets passed in. It says, all right, is the list empty? No, it's not empty. All right. So let's go to this part, return my list of 0. It's like, okay, that means that is the number 1 plus the sum of my recursion, sum recursion of everything that's left in the list, which is just the number 2, right? And that gets passed back into this function. Okay, so basically it's waiting for this to figure out like, okay, I have a list of 2 here, figure out what the sum is. This one's just chilling out over here. So we pass that list of 2. It's like, well, it's not empty. So we got in this condition, say return my list of the first element, which is 2, plus whatever the rest of the list is, which is an empty list. Okay, so we're waiting for this result. This gets passed into this result again, or into this function. It's an empty list, returns 0, pops back out. It's like, oh, okay, that's not an empty list. It's 0 now. And then basically this pops out again from way before. It says, oh, it's not a list of 2. This is actually just the numbers 2 plus 0. So just 2. And then it says, okay, cool. That means we had 1 from the very beginning, 2 over here, basically returns that whole sum, which is just, like I write it here, 1 plus 2, or just 3. So it'd return the sum of 3. Okay. So again, this is another way for you to be able to build with just if statements, essentially. You're able to go through that same list and add up all the sums. So it might be a little more be like, wait, why would I do it that way? Because I don't think most humans would think of this way immediately. But it's another option. It'll be useful when we don't know the structure. So you can see here, I run this through, and I can go through here, and I have our 4,950. If you look at this too, my executed time, it's actually a little faster in this case. I actually don't know. I believe if you get into larger numbers, recursion ends up being a little slower. So you can see that's 4 milliseconds, but this one's now 5 milliseconds. Okay, and I probably can increase this guy. If I increase it too large, it'll end up being way too long. Oops, I didn't put this on here. We can see now it's executing and it's reached its point. It's like, it's too deep. It's too deep. So again, recursion is built for different kind of stuff. You can get into some really big issues. So that probably won't execute either. I was just seeing what happens. It was close. 500. Okay, 500 is not bad. But you can see it goes exponential. So sometimes recursion does make sense, but you have to be careful of how deep it can go. And the reason why we pay for it is that we don't know what the structure is, and we pay for not knowing with essentially a little more execution time. So that's the one way you can think about it. Another function, just to kind of show you again, is a max loop. So if you had a loop, right, you wanted a for loop to create a maximum or find the maximum within a list, right, which obviously in this case will be 100, right? You can basically say, okay, let me go and start with saying, what is the current maximum? I'll start with the first number in my list, right? And then basically go through the list and compare my maximum that I have so far with the next number, right? And if it's bigger, that is my new maximum. If it's not, just skip over and keep using it. So if I had like, let's say 1, 0, 0, 0, 2, it'll go take my first number, 1, compare it to 0. Oh, 1's bigger, they're out 0. Next one, throw out 0. And then you get to 2, like, oh, cool, 2 is bigger. So go ahead and throw out 1, and 2 is my new maximum. And it goes through from there. So hopefully that kind of makes sense of like how you would probably look at how you would actually find a list. I think most people would kind of think about if I gave you a list of numbers and trying to find the maximum, you'd find the biggest one, remember that biggest number, you found a bigger one, keep that one. So you can see here, 1 through 100, well, or I guess to 99, right? 99 is the biggest one, duh. Okay. So if I do something similar with recursion, again, you can see here I have my stopping condition, right? In this case, you'll notice too, I had to add this extra part because I don't know what to start off with. I have to, by default, say, all right, by default, your current maximum is the lowest possible number. You can see here I had negative infinity. In case you didn't know, you can make negative infinity in Python, and it works like negative infinity. You can compare it with anything, and it will always be smaller except for negative infinity itself, which is kind of a fun thing to play around with. But it's a float, so you can actually do some comparison. So I can say, okay, if my list is basically, there's nothing in my list, well, basically you can kind of say like there's nothing in my list, so the smallest thing possible in there is negative infinity. So that will return negative infinity. So hopefully that kind of makes sense. If that's not what you wanted, if you wanted to return some of the error, you'd have to basically encode that outside of this function. Otherwise, I'll go through here and I'll get basically my potential max. It'll just take the very first element in the list, and then it'll do that same thing. It will compare with the potential max, okay, with what it had before. Okay, so the potential max with its current max, if it's the first time running through, it's be negative infinity, right? Current max equals potential max, and then it'll return basically the maximum of the rest of the list, which makes sense, right? If you were to say, like in a recursion list, or like say you have a list of numbers, you take the very first element, let's say that's like number 1, and then say, well, okay, what's the maximum of the rest of this list, right? If I know the maximum of this list, let's say the maximum is 3, all I gotta do is instead of comparing each individual one, I just gotta compare 3 with this 1. Of course, how do you know what the maximum of this list is? In this case, the solution for recursion is just return the same, basically take the very first element and compare it with the rest of the list maximum. So you can kind of see like you get this nested kind of view, which is why it works really well with XML and JSON, because we have a lot of nesting, okay? So if I run this now, let's clear all these drawings. You can see here, it should also give us 99, but it might take a little longer. So if I try this now, let's say let's try 1,000, okay? So you can see 3 milliseconds here. And this is just an extension. That's not normally built in. You can see, oh, it's getting a little slower, right? Let's try 5,000. Ah, slow, because it's too many people, or too much recursion. There's overload of recursion. So again, something to keep in mind. Now, again, these are bad examples because you probably would never find the maximum in this. It's not built for this kind of thing. There are certain languages that are built around recursion, which allow you to do some interesting things. And for example, there are things like functional programming languages like Haskell and OCaml that are basically built around recursion, but Python's not one of them. So this is something that you kind of have to keep in mind too, because it keeps everything in memory essentially, and it doesn't know how to deal with that. Okay, so that's kind of examples of recursion. So we can actually see how it handles general structures. So this is actually from Learn. If you tried running a for loop on this, as I will show you in a second, it's not going to work because you can see there's nests within nests, but we don't know how deep those nests go. So if you try running this, it tried doing it, but then it failed, right? Because it's trying to go through each element. Well, you can't add a list by a list. So if I tried doing, like, for example, print X, right? You can see the first element's 1, which is awesome. But the second element is a list, and we can't just add a list. You could then maybe say, okay, well, if it's a list, go deeper into it. But what if we have a list within a list within a list? Then we have another part in there. It's like, what if there's a list and a list and a list and a list? And like, when you're going to have 4 parts in there. So you can imagine this for loop getting very structured, and you never know if you're actually completely done. This is where recursion's super useful. And we can actually have it here. This, oops, sorry, I made it small. This here, same idea. We still have this L, right? And we can define this function, basically say, okay, what you're going to do, and in this case, I put this print so you can actually see what's happening. Basically says, all right, if basically there's not this isn't, what's it called? Not L, basically I'll also say it's not 0, it's not an empty list, you can return 0. Otherwise, you can say, all right, if this first element in the list is a list, okay, we're going to do my sum on that first element. So if it's a number, we can actually do something with that. Otherwise, I'll do the my sum of that part, right? So you can use these things, and then otherwise you can do the same thing. If it's not a list and it's not an empty list, right? We can go ahead and say, all right, just get the very first element plus whatever's left in that list, okay? So you can get this nested part. So basically you have a few conditions. One is that if it is essentially a list or an empty list, the empty list should have nothing in it, right? 0. Otherwise, if it is a list, right, we can say, all right, take the very first element in the list, figure out what the sum is, and then take the rest of the list and figure out what the sum of that is over there, okay? And then otherwise, if we actually have a number, we just get the first number in that list and proceed forward, okay? So if we run this now, you can see, and this is from the curriculum too, is that you can see we have our very first L right here, okay? And it's going to take that very first element, which is just 1, and then that second sum, right? This second sum right here, say, all right, take the sum of this guy right here. And say, okay, it finds the first element is a list, which is this guy. And then it's like, okay, let me get the first element, it gets 2, it gets the rest of the list, it's 3, 4, 4, empty list, right? It returns 0. So it basically pops out, okay? And it pops out to number 5. It knows how to deal with 5. The next part is that 6, 7, 8 goes through here. Basically, you can kind of see every time you see that empty list, it reaches the end of that internal list, pops back out. So in this case, you can see there's a list of 7, 8, and 9. So it goes into 7, 8, gets to 7, gets to 8, empty list, goes back out to 9, and goes forward. And then at the very end, when we have nothing else in the list, it's the end of it. So we basically get that whole sum. Essentially what we're getting is that whole sum here, plus this little 0. And it ends up getting 45, okay? Which, if you have this all flattened out, you would be able to do that. So again, you're able to do stuff with recursion where you're essentially saying, I don't know what the structure is, right? But if you keep repeating the same thing, basically a list is very self-similar, like nested lists within lists. It's like, oh, well, you know how to calculate the sum for that nested list. If we know how to calculate the sum for this one, and then say, okay, let's expand it out. It's like, well, if we come across another list within a list, we can say, all right, let's do the sum of this internal part and so on. So that's why we would use recursion over something like a for loop. Makes sense? Again, this stuff is not super easy to grasp, in my opinion. But how are you guys feeling that? Thumbs up so far? Thumbs down? Sideways? Yeah. I'm with you on sideways. Sometimes recursion can just be like, what is going on? But just know that you can do recursion basically by doing self-similar parts. And that's why we use it for JSON and XML, because you can have basically nesting, things that are very similar to each other. Okay. So one thing I did want to mention before we kind of end up is depth versus breadth. This was actually pointed by the curriculum, I think, for brilliant.org. It kind of shows you what a depth versus like a breadth is. Basically know that you can kind of go two directions. One way you can go is basically go as deep as possible. Okay, like go as deep as possible before popping out, or you can go outward as much as possible before going deeper. So that's what the breadth is versus going deeper in. Going deeper is kind of like if I said, okay, I have this list right here, and I've come across, instead of, I find like, how deep does my list go? And I'll go, okay, let me go as deep as possible and then pop out. Breadth first would try to do, what's the sum of this one? What's the sum of this one? What's the sum of this one? What's the sum of this outside part before going in deeper? And then it'll go forward. So you can structure it differently. So you can see here breadth example from learn.co. So this one is a similar my sum part, but in this case, this was a depth in first. Basically, once we hit something, we go deep into it. We don't stop until we basically we exhaust all the parts of that nesting, and then we pop out. The breadth one, instead, we're basically kind of going layer by layer. So we essentially say, all right, what's this first one here? What's this next one here? What's this next one here? Next one here before we go in deeper. So just know that it'll end up being the same number. I won't go far into this, but you can see here is that the different execution part, you can see it basically is like, oh, all right, let me get this one part, cool. It gets the 2, 3, 4 part, it's this part. So you can kind of see that it ends up essentially doing more at the levels versus actually going deeper, where this one essentially was trying to basically divide and conquer. It was going in deeper and deeper and deeper until it can figure this one out. Once it figures it out, then it pops back out and goes to the next level, or the next like side level, if that makes sense, versus a deep level. So yeah, fun thing to kind of know about. There's a whole bunch of examples you could probably find about recursion. If you're curious, again, this is a good resource right here. It kind of shows a little bit about like, what these things are. There's some advantages of going breadth first versus depth depending on your situation. So yeah, cool. Any questions you guys have? Do you even know what kind of questions you could ask right now? I don't know, but yeah.
There's a library for more of the web scraping part, necessarily the recursion part, right? I think it's called Beautifulsoup.
Yes, and we'll talk about that too. I think next week is Beautifulsoup is. I think it's one of the sections we just released. And what's it called? That one, what's kind of nice is that you usually don't have to worry about it as much. But just know that this is how it's structured. And if you come across data, let's say someone does some random, some random data structure that is like separated with, I'm trying to even think something that you can give something and it wouldn't, like, honestly, like if you have a comma separated values or something that's like, if you have a structure of like JSON that's like this, but somehow they use like weird funky characters and stuff like that, you probably could just like be able to feed it in with basically saying, well, treat these things as these elements. But if you came across a structure that was unknown to you or doesn't have a library, you can use essentially a recursion part. But yeah, for the most part, we probably will use something like Beautifulsoup that can process HTML, which is again structured very similar to XML, and we have that nesting feature in there. But yeah, for data scraping, we'll probably use Beautifulsoup. At least that's what I use personally. There's other tools you can do. That's pretty popular. This is much more like if you have like if you have a file that has a certain structure. And I think Beautifulsoup can actually process XML files. And if you have JSON, you can just use the built-in JSON library. But But yeah. I don't know if that wasn't really a question. That was more of a comment, right, Josh? That thing.
Yeah.
Okay. Cool. Yeah. Anything else you guys want to say about this, or okay. Cool. All right. So I'll go ahead and stop recording.